In 2015, there was a climate summit that was held in Paris, France, in which the party nations agreed to try to limit carbon emissions to prevent what they call dangerous global warming, which they had pegged at we want to try to limit emissions. All these nations are going to come together, we're going to try to limit emissions such that global temperatures don't rise more than 2 degrees Celsius by the end of the century. So sometimes we'll hear the 2-degree target or the Paris target. That's explicitly what it's referring to. And a 2-degree warming doesn't sound like a lot to us because when you guys woke up this morning, assuming that you were up within 3 hours when I was up, I was up at 5 to 6. So you guys are up early. By the time we're in class, temperatures change more than 2 degrees Celsius. It's gotten warmer. Amazing. And so like we think of these changes of 2 degrees or 3 degrees or 4 degrees as relatively small. You think about like temperatures in July and August compared to now. That's like 10 degrees, 20 degrees Celsius. So a 2 degrees Celsius can sort of sound very small. And we sort of have trouble wrapping our brains around how big that kind of change can be. David Monroe, who does the brilliant comic XKCD, which you should all check out online. You won't get all the humor. I don't get all the humor unless you're into linguistics and computer code and science, biology, physics, chemistry. He sort of writes about, or in this comic, writes about the idea of an ice age unit as a way of trying to represent climate change. So here we are. Here's David Monroe and where he lives. This is his neighborhood. So average modern times. Where we are today, we've sort of slid a little bit over in terms of ice age unit. Where we'll be in 86 years, possibly up to a shift in 1 ice age unit in his neighborhood. Right? One ice age unit warmer. Now, going from now to 1 ice age unit warmer doesn't make a lot of sense unless you go from now to 1 ice age unit colder to 20,000 years ago, where his neighborhood is under basically a kilometer of ice. So a relatively small change of about 4.5 degrees Celsius will change being under 1 kilometer of ice in an ice age to birds and grass. And again, small change leading to these relatively big changes. And if you want to really try to stretch your mind, if you go back 2 ice age units, we go back to a period approximately 480 million years ago, during a period known as Ordovician, at the end of which most of the planet was covered in ice. It's a period called Snowball Earth. I'm sorry, that was 4 ice age units ago. So just, let's see, 4.5, 9, 18 degrees Celsius colder, very, very cold, almost uninhabitable Earth. Go just 2 ice age units hotter, up to 9 degrees Celsius, leading to conditions we haven't seen since the dawn of the Tertiary. I'm pointing at you, not that you necessarily do, but you had mentioned it earlier. So the end Cretaceous period, sea levels are much hotter or much higher. There are no glaciers on Earth. Palm trees at the poles. Good times. You can take spring break and go on up to the Arctic Circle. So, the only lesson here, just in terms of global temperature, small changes can have relatively big effects. That's the only lesson we're trying to get across. Now, sections 2 and sections 3 of Semitext really largely concern themselves with 2 components of climate change. Section 2 is on the idea of detection. Section 3 is on the idea of attribution. So, we're going to spend some time thinking about detection and the idea of how does one go about detecting changes in the overall temperature of the Earth. It sounds relatively straightforward, but when you drill down into it, it's actually not at all. One of the big challenges in trying to detect changes in climate is a phenomenon called weather. Climate would be really easy to understand, except for weather isn't weather. And weather is sort of the day-to-day changes in sort of what we experience outside. Climate refers to sort of long-term averages of what we expect. Where we live in the world, our climate dictates more or less that we have hot summers, we have cold winters, we have a period of about 3 months where the ground is periodically frozen. And that's not true of all places in the world. In the tropics, there's never a winter period where things freeze. But here there is. There's this sort of really strong seasonal environment. So as a result, we can have sort of what they've experienced in New England in the last couple of years. Like 2 years ago, they had like the coldest winter on record, which was followed by like the wettest spring and the hottest summer. And when you have sort of all this noise going on, it becomes really difficult to sort of disentangle year-to-year changes or month-to-month changes with sort of the broad climate trends. So how do we distinguish year-to-year variation from an actual trend? Fundamentally, we need some sort of tool that enables us to detect trends or engage in trend detection. All right, so definition coming at you probably from Civitext. But detection refers to a process of demonstrating that climate has changed in some defined statistical sense. So when we're talking about climate change detection, we need some sort of statistical criteria that allows us to determine whether or not climate has actually changed. So it's the process of demonstrating that climate has changed in some defined statistical sense. Absolutely no concern for what might have caused the change, just the question of has the climate changed. Right, so how do we, thinking back to the Civitext, what are some of the ways we can actually detect changes in climate, even given sort of the year-to-year variability we see in temperature fluctuations? Some of the ways that we can detect. Yeah.
We take data over a long period of time.
What's wrong with a short period of time?
Your certain changes will your weather won't get affected more. Because if you have it over a long period of time, this is more like the weather just might average itself out. No change.
So you're saying like you would like criticize me if I were to say we've been in a global cooling trend since 2016.
Yeah, that's a little bit.
That's not really climate, right? That's year-to-year variability. How much time do we need to sort of detect a change?
It depends how bad the weather is.
Okay.
How variable weather is. If the weather is relatively stable, then you need a shorter period of time.
Okay, so with two components of detecting change. First of all, longer is better because longer time series allow us to find trends that might not be apparent in short time series. And then secondly, variability year to year, sort of the noisier or the more variable it is year to year, the longer the time period you're going to need to detect a change. You can almost think of this in terms of your GPA. I'm very concerned about your GPA. Now, you might be the kind of student that's pretty consistent, 1 semester, 2 semesters, 3 semesters. Your GPA might be varying by about, a 0.2 or a 0.3, right? Because you're a pretty consistent student semester in and semester out. But there are other students, where for all kinds of good reasons, and then sometimes reasons that aren't so good, you might go from a 3.5 to a 2.7 to a 2.2 to a 3.7. Don't be smiling at me. I'm not saying this is a good thing. But you've got the variability built in because you had to work, you had to take care of someone, you slacked off, you got sick. All kinds of reasons can sort of come into play that can sort of account for that variability. So, if you were one of those consistent students, I could ask you, consistent student, what's your GPA last semester? That might be sort of a good indication of what you're going to get this semester, what you're going to get next semester. But if you're one of those students with a bouncy GPA, this semester is not going to be predictive of what you're going to do next semester or next year, or predictive of what you did last year. And it's sort of the same general idea with climate. The more the temperatures change from year to year in a given location, the harder it is to discern an overall trend. So in Simultext, the whole signal to noise exercise basically addressed this idea of detection. So we've got basically our two tools. The longer the time series, or the longer the number of observations we have, the better our ability to detect change. And also, and it's not anything we can control, but it's intrinsic to the data itself. The less noisy that is, the less variable that data is from year to year, or from period to period, the easier it is to detect the change. So if we were interested in trying to detect changes in global climate, try to get some sort of measure of shifts in temperature over time, where should we look? Or what should we measure to try to find a change?
We could use things like proxies, such as tree rings or the lithosphere, rock layers.
Okay, so one possibility is we can use proxies. Let's hold on to that one for now. Come back to it. It's not my go-to. Yeah. Okay, stick a thermometer outside and measure the temperature. Sounds easy enough. It's a lot more complicated than that. However, what we could do is we can look at measured air temperatures today and yesterday, the day before, all the way back until sort of when the first temperature records were kept. Advantages of that approach. We could read a thermometer, right? So we've got really good data. Disadvantages. The location of thermometers is not evenly spread across the Earth. You have more thermometers in Dayton, Ohio than my friends down in the Madre de Dios region of Peru. The Machinega people live in small villages. They don't have thermometers, right? You could spread over an equal area. We've got lots of records here, none from there. Likewise, temperature records from Beaver Creek don't go back nearly as far as temperature records from Philadelphia. Why is that? Haven't been around as well. So we've got a distribution of thermometers that's non-random. We won't even talk about the ocean right now. We're measuring out in the middle of the Atlantic in 1982. So we have very uneven coverage of where those thermometers are, and the records from year to year, some go back really far, some only go back 20, 30, 50 years. So you can spend a whole career trying to optimize how to deal with the temperature records from thermometers. And we won't even get a thermometer replacement. So we can measure the air temperature with thermometers, but that in and of itself is not going to give us a good indication of changes in climate. What we'll keep is good. It's not good.
measures of drought and rainfall in African areas?
We could use measures of drought and rainfall, although that gets very complicated because different areas have different precipitation regimes. And trying to average anomalies over broad areas of precipitation is complicated. So it's been very difficult to use information from the hydrosphere for assessing climate change. What else we got?
Changes in the cryosphere?
The cryosphere, what's the cryosphere?
That's looking at glaciers, icebergs, essentially what is frozen in ice.
Okay, so if the climate was cooling, what would you expect to see?
You would see an increase in average area covered by ice sheets.
So you can see an increase in the area covered by ice sheets. You can see an increase in the volume of ice sheets. Okay, so that's ice that's basically being locked up. Okay, and what would we see if, rather than cooling, if the climate was warmer, what would we expect to see?
You would see decrease in volume, decrease in surface area covered. Okay.
And where would that water go? All right. So let's talk about the. All right. So another place we detect climate change will be in the ocean in terms of sea. In terms of
How high the sea is.
okay. And do you remember the two causes of what causes sea level to go up? We've got more water from glaciers is one.
Thermal expansion.
Thermal expansion. Okay, so as water gets warmer, it sort of expands. Not a lot, but when we're dealing with quadrillions of gallons of water, a little bit of expansion can make a big difference. Okay, so we can look to the oceans as well. And what else could we look at?
You can look at tree rings.
We could look at tree rings, and that's getting back at past climates, the idea of proxies, which we're gonna put a hold on for now. Look at the proxies soon. So one last thing we could look at is not necessarily tree rings from the past, but we can look at the biological responses of organisms in terms of date of first flowering, periods of migration, and look to see whether, I think in the semitext, they talk about sort of the lengthening of growing seasons, state by state in the US. I think everywhere outside of the southeastern US, the growing season is getting longer. Okay, so the idea that you've got these biological responses taking place as well. Okay, so we've got the atmosphere, we've got the cryosphere, we've got living organisms, and we've got the sea, all of which are potentially useful in detecting climate change. So with atmospheric temperature, we've got reliable, I'll put reliable in air quotes, we've got more or less reliable data that goes back to about 1870, 1880. And that record has gotten better through time as we've added additional data. It's, the air temperatures are sometimes referred to as the instrumental record, because the thermometer is a scientific instrument for recording temperature. And what we see sort of over that period is roughly about a 1 degree Celsius warming since 1880. Now, rather than talk about the globe going from 18 degrees Celsius to 19 degrees Celsius, or whatever the specific term is, scientists tend to report things as temperature anomalies, which is a really weird way to think about temperature. But as explain the CE text, an anomaly, a temperature anomaly, is basically a deviation in the temperature from an expected value. So in this particular graph, we have an expected value, or we sort of set the 0 line, no anomaly, and the average global temperature for all the years between 1900 and 2000. And so we basically set that at 0. And then in a year when the global temperature is below that 20th century average, we sort of drop down below the line. And when it's above the average, we sort of shoot above that 20th century average. And a couple things sort of jump out of this graph at me. Certainly it looks like the period from 1870 to 1930 was cold. We sort of had this consistently colder than average. Things bounce around from the 40s to the 70s, and then from the 1980s on, it got warmer. Although this can be a little bit misleading, because if there's been a gradual increase in temperature over time, you would expect cooler than average temperatures early on, and then sort of warmer than average temperatures later on in the time series. So it's not necessarily that these older periods were necessarily colder, they were just cold compared to where we are now. The second thing that sort of jumps out at me, it's weird that in my lifetime, I've only experienced 3 years that were colder than average in the 20th century. And I sort of distinctly remember them, although I don't really sort of try to impose sort of my own story growing up in Philadelphia in the 1970s, being small and feeling cold, with sort of the global average, because Philadelphia is not the globe. But basically 3 years were colder than average, and then all the rest of the years have been warmer than average in my lifetime. But I think, sort of without exception, everybody in this room has lived their lives in a warmer than average year, at least average for the 20th century. So you've never experienced an average year in your lifetime in terms of temperature, if we consider average to be the 20th century global warming. All right. So what about before 1880? Are you ready? Okay. Ready for keyword? Prior to 1880, prior to the instrumental record, we could still measure temperature, but we can't measure it as well. And by saying not as well, we cannot measure it as precisely. Now, there are all kinds of things that respond to temperatures, like tree ring growth. In a colder year, trees are going to grow slower. In warmer years, they're going to grow faster. And so we could actually use tree rings as sort of a stand-in or as a proxy for temperature if we don't have any actual records of temperature from that time period. The idea being that we can sort of standardize things that are very little growth of a tree would indicate a colder year, the bigger ring would indicate a warmer year. Some problems with this approach. One of which is it's not just temperature that affects growth. Precipitation can affect growth as well. And disentangling the effects of temperature versus precipitation, available moisture, could be a little complicated. So as a result, our estimates based on tree rings of past temperatures are not quite as good as we'd expect from just straightforward temperature alone. There are other proxies as well. For example, we can use growth rates of corals in the ocean, which respond to water temperatures. We can use stable isotopes of oxygen, which reflect atmospheric conditions and the rate at which these isotopes form and decay. No one of them is particularly good. But if you take several different independent proxies, you take a coral reef record, and you take a tree ring record, and you take information about other types of proxies, and you sort of stick them together, what we can do is basically create what's called a multi-proxy, or a proxy record based on several different kinds of proxies, and get a rough estimate of past temperatures. So if we go sort of back to 1880, each one of these solid lines represents a different series of proxy records, and each of which is a different study. And you see there's a lot of variability, not just within. So here's a green EID land with uncertainties. So this is showing sort of this particular proxy and its variability, or its range, which is giving us something very different than what we see in the orange line and in the magenta line. They more or less track, but there's a lot of variability even among these proxies of about 0.6 of a degree Celsius right here in terms of that range. So proxies, not as good as the instrument, but can help us get broad trends in temperatures from time periods past. All right, so we can see here, 1,000 years back with these multi-proxy records, it looks like you have variability from century to century, but what appears to be happening since 1900 appears to be perhaps something new. Any questions on proxy records?